Is it working?
Yes. So it's now 10:50, so let's start today's first parallel session, session 1A cosmology. The first speaker is Chanshu Lu, and she will tell us about spillway preheating and efficient particle production mechanism. Please start.
Thank you. I'd like to thank the organizer for the opportunity to speak and also dealing with the difficult time zone difference issue. So today I'll be talking about spillway preheating, which is a new mechanism we're proposing that can be used to deplete inflaton energy density after inflation. And it is more efficient at doing so compared to existing preheating models in the literature. This talk will be based on work I did with Gigi Fan at Brown and Chloe and Lozenov at UIUC. So in order to connect the inflationary epoch with Big Bang cosmology, we need to get rid of the inflaton after inflation. A simple way to do this is to simply couple the inflaton to some daughter fields, therefore generating a perturbative decay width of the inflaton that will slowly get rid of the inflaton energy density. Now, in terms of a very cartoon picture, we can imagine the inflaton being a tank full of water, and having a perturbative decay width simply means that there is a small hole in the bottom of the tank that is slowly leaking water away. But it's been known for a very long time that this very simple picture is often not the full story, because the inflaton can be oscillating around the minimum of its potential after inflation. This oscillation can drive the instability in the system, causing a resonant production of the daughter fields that's much faster than what you naively expect from calculation of the inflaton perturbative decay width. This nonlinear phenomena was named preheating, and many different models of preheating have been found and proposed and studied in the literature. Now, coming back to our water tank analogy, what preheating does is that now we have a daughter field tank next to the inflaton tank, and preheating simply removes a large portion of the wall, allowing water to rapidly flow from one tank to the other. Now, this all sounds very good, but existing preheating models in the literature share a common problem, is that when the daughter fields accumulate a significant energy density, its back reaction on the system shuts off the instability and prevents further transfer of energy out of the inflaton. This is just like how the water is going to stop flowing once the water level is flat in the large tank. So existing preheating models in the literature leave anywhere between 1% to 50% of residual inflaton energy density. And by residual inflaton energy density, I simply mean the ratio of the inflaton energy density to system total energy density at the end of preheating. Now, what this means is that ultimately, we still have to rely on the slow perturbative decay of the inflaton in order to get rid of a significant portion of the inflaton energy density after inflation. Now, our spillway preheating mechanism is based on the observation that if in the system there exists a spillway, as shown here, that can be used to get rid of the excess energy density in the daughter fields, this will alleviate back reaction on the system and allows more energy density to be transferred out of the inflaton. Of course, this is a very simple cartoon picture that I'm showing you here. So for the rest of my talk, I will be showing you actual models, actual field contents and interactions, and giving you results from concrete numerical simulations. But before I do that, just to give you the punchline right now, using spillway preheating, we were able to achieve a residual inflaton energy density of only 0.01%. So that's a significant improvement compared to existing models in the literature. And we also found that spillway preheating mechanism has a very nice feature that the residual inflaton energy density scales as an inverse power law with one of the model parameters, meaning that the mechanism has a potential to be even more efficient depending on the parameter values you choose. Okay. So here is the outline of my talk. As I promised, I will start talking about our actual models in terms of field contents and interactions, and show you numerical simulation results to support all the claims I have been making about the efficiency of our spillway preheating mechanism. And before I conclude, I'll briefly touch on the assumptions we made in our numerical study and the range of parameters for these assumptions to hold. Now, in terms of field content, our model is actually very simple. We have phi a scalar, which is the inflaton. We assume its minimum of the potential after inflation is quadratic. We have a daughter scalar field chi with a trilinear coupling between the inflaton and the chi field. And to stabilize the potential, we give a self-interaction to the chi scalars. And we also have another daughter field that is psi, which is a fermion. And we give a Yukawa coupling between the chi daughter field and the psi fermion daughter fields. Here I have written the trilinear coupling between the inflaton and the daughter fields in a very suggestive form, where I have factored out the initial oscillation amplitude of the inflaton, capital phi naught, making it manifest that capital M is really the typical mass scale for the chi fields. So clearly, as the inflaton oscillates around the minimum of its potential after inflation, this trilinear term is going to act as a time-dependent mass term for chi, the chi field. Now, it is known for a very long time in the literature that this time-dependent mass term for chi is going to cause a resonant production of the chi field when certain condition is met. This condition is on this resonant parameter, which I call Q, that is defined as the ratio of the mass, typical mass scale of chi to the inflaton mass, multiplied by the ratio of the inflaton oscillation amplitude at any given point in time to its initial oscillation amplitude. So whenever Q is big, the Q parameter is bigger than 1, and we are in the linear regime, people have found that there's going to be resonant production of chi. Now, this resonance was found by these authors in 2006, and it was named the tachyonic resonance. I'm coming back to my water tank analogy from before, but clearly the scalar part of the potential is our water tank. We have the inflaton phi and daughter field chi with a tachyonic resonance connecting the two tanks. And our spillway is simply the perturbative decay width to the chi field that is generated by this Yukawa coupling between chi and the psi fermion. Okay, so as I have been implying for several times now, preheating is a highly nonlinear dynamics that can only be studied using numerical methods. So that is what we did. We used a modified version of the lattice EZ program, which is a program that studies system evolution by solving the classical equations of motion of the scalars. And we have modeled our fermion psi in our system using as a perfect relativistic fluid. Okay. Here, I have chosen model parameters such that we assume that the inflaton inflationary potential is quadratic. We give some moderate hierarchy between the two mass scales, and we have chosen some Yukawa coupling just to be specific. And in this plot, I'm showing you the evolution of the co-moving energy density of the three fields as a function of the dimensionless time. Okay. So what are we seeing here? At the beginning, it's a bit hard to see because the curves are overlapping, but there is a very rapid production of the chi scalar because of the tachyonic resonance. And subsequently, there's a rapid production of psi from decay of the chi particle. Now, if there is no Yukawa coupling, if there is no spillway, once the chi energy density becomes comparable to the inflaton energy density, tachyonic resonance will be shut off and energy transfer will stop. However, thanks to our spillway, which is continuously moving energy density out of the chi field into the fermion psi, we were able to transfer more energy out of the inflaton using the tachyonic resonance, as shown here. But of course, as this chain of energy transfer continues, at some point, we would have depleted so much energy density out of the inflaton that its oscillation amplitude is so small that it can no longer sustain the tachyonic resonance. And this is what's happening at this point. So after this point, tachyonic resonance is truly terminated. So spillway preheating has ended, and there's no more energy transfer out of the inflaton. And we see that in this specific example, we have achieved a residual inflaton energy density, shown here, which is at the level of 1%. Now, of course, 1% is already competitive with existing models, but I have promised you a 0.01% efficiency. Now, in order to understand how we get the 0.01% number that I have claimed, we need to understand what is the physics. Sorry about that. We need to understand what is the physics that dictates this number. So remember, I keep saying that we have energy transfer. Here we have an energy transfer pipeline from the inflaton to the chi field and from chi to the psi field. And really, ultimately, what's driving this whole energy transfer process is the tachyonic resonance from the inflaton to chi. I'm going to skip the slides. So let's go back to what is the condition for this tachyonic resonance to happen. I have briefly touched on this condition here. So in the linear regime, people found that tachyonic resonance happens when this resonance parameter is bigger than 1. So this resonance parameter was defined here. Now this ratio of capital M to small m is simply a model parameter that we can define it to be. I have been calling it Q0. Here, another quantity is the ratio of the inflaton oscillation amplitude at any given point in time to its initial oscillation amplitude. Now, clearly, this quantity is time dependent, and it can have complicated time dependence. However, we can approximate this ratio of oscillation amplitude if we assume that the energy density in the system is dominated by the inflaton mass term. And then we can approximate this ratio of inflaton mass term as the ratio of inflaton energy density to the system total energy density. Now, under these assumptions, and if we define that the spillway preheating ends when this parameter becomes less than 1, the conclusion we achieve is that the residual inflaton energy density is going to scale as Q0 to the power of -2. Okay. Now, of course, this is a very simplified analysis. We assume a condition that only applies in the linear regime, and I have made some assumptions to calculate this ratio of the oscillation amplitudes in terms of energy densities. However, amazingly, we found through our numerical simulations that this power law is actually true in our system. So here I'm showing you the residual inflaton energy density as a function of the parameter Q0 for this specific choice of Yukawa couplings. We see that indeed the residual inflaton energy density do follow an inverse power law with Q0. It's just that the power is not -2, it's about -1.3. But this shouldn't be surprising because, as I said, the Q0 to the -2 was derived from a simplified linear regime analysis. But through numerical studies, we found that even though the exponent is different, the inverse power law scaling is still true. And the 0.01% residual inflaton energy density that I have been promising you is achieved by this point here, where Q0 equals to 200. And I have shown you a plot for this very specific value of Yukawa couplings, but similar scaling law was also found for smaller values of the Yukawa couplings with slightly different exponents. Okay. So before I conclude, I just want to touch briefly on the assumptions made in our numerical study and their validity. So I have mentioned briefly that in our numerical study, we were solving classical equations of motion for the scalars, and we have modeled our fermions as a perfect fluid. So that is making assumptions about the occupation number of the scalars and also the strength of interaction between the fermion and the system. I won't go into the details, which are spelled out in our actual paper, but just to give you the conclusion, it turns out that spillway preheating really only safely works when you couple not only one fermion to chi, but instead couple NF species of fermion to chi, where NF, the minimal required value of NF is determined by lambda, which is the self-interaction strength for the chi field. And we have a constraint on the Yukawa coupling between the chi field and the fermions in terms of NF and lambda. Now, to conclude, hopefully I have convinced you that spillway preheating is a new mechanism that can be very efficient at transferring energy density out of the inflaton after inflation. It has this very nice feature that its efficiency scales as the inverse power law with one of the model parameters, which is the Q0, with Q0 to the -x, where x is close to 1. Now, it will be interesting to see what kind of effects spillway preheating has on cosmological observables, such as curvature perturbations or gravitational waves. it would be also interesting to think about if there is any application of this efficient particle production mechanism outside the context of reheating. Thank you very much.
Thank you for the presentation. Are there any questions? So let me begin with questions. What is the difference between the instant preheating scenario?
Yes, that is a great question. So in terms of setup, in terms of just the field content, spillway preheating is very similar to instant preheating. Although they have a different resonance here. So they talk about a phi-squared chi-squared coupling instead of phi chi-squared, but that's not hugely important. But instant preheating has a criteria. Instant preheating is aiming to complete preheating without even having the inflaton oscillates. So it really requires this Yukawa coupling between chi and psi to be really tuned to match the inflaton oscillation. But ours is different because, as you can see here, we are going through hundreds, order 100 inflaton oscillation amplitude. And we don't require this fine tuning for this energy transfer efficiency, for this very efficient energy transfer. So in terms of field content, it looks similar, but ultimately we're trying to achieve different things, and the two models work in very different regions of parameters.
I see. Interesting. Are there any questions or comments? Oh, Masaki, I don't know how to allow, maybe staff allow you.
Can I speak?
Yes, please.
Okay, so you take a relatively large Yukawa coupling, but how the efficiency depends on the Yukawa coupling?
Yeah, so I showed you this plot, which is for, yes, relatively large Yukawa couplings. But here, I hope the plots are large enough to see. So we went down to the smallest Yukawa coupling we tried was 0.01, as you can see here. So as you go to very smaller Yukawa couplings, you see the curve is kind of, the line is kind of moving up. So the efficiency is getting worse, which is reasonable because in the limit of the Yukawa coupling going to 0, you should have very bad efficiency. So in general, if you go to smaller Yukawa coupling, it's going to have worse efficiency in the fact that the curves are moving up. But you see that we still have this inverse scaling with the Q0. So even with a small Yukawa coupling, for a relatively large Q0, you can still be very efficient compared to the case where the Yukawa coupling is 0.
I see. That's interesting. Thank you very much.
Okay, are there any questions or comments? So the cubic interaction, there's Q&A. So there is a question, why the back reaction from fermions can be ignored?
Yeah, so in the numerical simulations, we have in the numerical simulations, we have modeled the fermion as a perfect fluid, so we were effectively ignoring it. But as I have tried to list out here, in the actual paper, we have talked about the fermion back reaction. We try to approximate it using analytical expressions. So there are a few, so let me go back to the potential. Yeah, so there are various back reactions. First of all, this Yukawa coupling can obviously be a mass term for the fermion. And if the mass term is large, the chi can no longer decay into the fermions. So that's one criteria. And second thing is that this psi bar psi can have a vacuum expectation value, making this a tadpole correction to the scalar potential. So the numerical simulations do not capture these effects because of the lack of technology in simulating fermion interaction with everything. But in the paper, we have estimated these effects, and here the strange condition that we need to couple NF species of fermions really comes from the criteria that we have to suppress these fermion back reactions, because effectively you see the higher effectively, by coupling NF species of fermions, what we are saying is that the Yukawa coupling here is no longer the individual Yukawa coupling. It's the sum of all the Yukawa couplings of the fermions. So when NF becomes large, the Yukawa coupling is actually becoming small. So yeah, we have considered these fermion back reactions, and this is why we need NF species of fermions to make it valid that we are ignoring them in the numerical simulations.
Okay, so let's thank Jianshu.
Thank you, and thank you for the questions.
Let's move on to the next talk. Then Masaki Yamada will talk about cosmic biorefringence triggered by dark matter domination. Please start.
Thank you very much. Thank you for the opportunity to make my presentation today. I will be talking about cosmic birefringence triggered by dark matter domination. So this work is motivated by the recent analysis by Minami and Komatsu, where they have found hints of a faint Barifringence signal in the Planck data. So what is Barifringence? The cosmic Barifringence is the rotation of the polarization plane of the CMB photon, something like this. So as you know, the standard cosmology predicts only A modes, like this. But if the polarization plane is rotated after the last scattering surface, then we get a nozzle B mode. So the observation of the EB correlated power spectrum implies that the polarization plane is rotated after the last scattering surface. So this is known as the cosmic Barifringence. And this would be a hint for the physics beyond the standard model. So this is a quite important parameter in the CMB. And recently, Minami and Komatsu have found hints of a faint Barifringence signal in the Planck data by using an approach to mitigate certain systematic errors. And according to their analysis, the isotropic Birefringence angle is equal to 0.35 plus minus 0.14 degrees, which corresponds to the statistical significance of 2.4 sigma. So this would be a hint for the physics beyond the standard model. So it would be interesting to understand what kind of physics beyond the standard model can explain this Birefringence signal in the Planck data. So in our work, we focused on string axions, or simply axions. The axions are predicted in the string theory in the low energy EFT, and they may have very small masses because of the shift symmetry, and they may couple to photon via chance-Simon coupling. So this FF tilde is the photons, and phi is the axion. And F phi is the axion degree constant, expected to be over the cut scale. And the axions leads to rich phenomenology in cosmology and as well as particle physics, depending on their masses. For example, if an axion is very heavy, it may be an infraton. It can be a infraton. Or if the axion mass is within a certain window, its coherent oscillation can explain the cold dark matter. But in this talk, we focus on a very light axions. And actually, such a very light axion can predict the cosmic Barefringence. The cosmic Barefringence can be induced if an axion moves before present and after the recombination epoch. So this can be understood by looking at the Lagrangian. So this is the kinetic term for the photons, and this is the chance-Simon coupling for the photon and the axion. And this FF tilde is something like a E dot B. E is the electric field and B is the magnetic field. So this is E dot B. And the first term is the E square minus B square. So we can complete the square of these terms in this way. Then you can see that this combination and this combination satisfy free wave equations in vacuum. So this means that if the field value of the axion changes, then its polarization plane is rotated by a factor of this combination. So the Barefringence angle, or the rotation angle of the CMB photon, is given by this formula. where delta phi is the difference of the field value of the axion between the recombination epoch and the present. And if the axion moves after the recombination epoch, we expect that this combination is over the unity. So the resulting Barifringence angle is of order 1 or 0.1 degrees. And actually, this is consistent with the Planck data. So we don't need any fine tuning in the misalignment angle to explain the Planck data. And the axion decay constant can be arbitrary because this combination is expected to be over the unity. So the axion decay constant can be as large as a Scott scale. So this axion can be the string axion. So this is a very interesting and simple scenario, but this axion have to move before, present, and after the recombination epoch. So this means that the axion mass should be larger than 10 to the minus 33 electron volt and smaller than 10 to the minus 28 electron volt. But there is no reason that the axion mass is within this window. So this is a kind of another cosmic coincidence problem. So the question is why the axion starts to oscillate just before the present epoch. And we'd like to answer this coincidence problem, and this is our proposal. So we can address this question by introducing an effective mass for the axion that is proportional to the dark matter density in this way. So here h squared dm is given by the dark matter density. So this term is negligible in the radiation dominated era because dark matter density is negligible in the radiation dominated era. But this term becomes relevant in the matter dominated epoch because Hubble square dm is comparable to the Hubble square, right? So this means that this mass term, effective mass term, triggers the axion oscillation after the matter radiation equality. And since we know that the matter radiation equality is just before the recombination epoch, so this explains this cosmic coincidence problem. Okay. So we explain the cosmic coincidence problem thanks to the coincidence of the matter radiation equality and recombination epoch. Okay. So this is our proposal. And I will show you later about the UV complete model of this effective mass term. But before that, let me show you the resulting Barifringence angle in this model. So the low energy effective field theory is very simple. We have a kinetic term for the axion, and we introduce a effective mass term that is proportional to the dark matter density. And we have a chance thermal coupling to the CMB photon. And the red figure is the resulting Birefringence angle in this model as a function of CH. CH is a coefficient of the effective mass term. Okay. And here we assume that the initial misalignment angle is equal to unity, but this can be as large as pi. Okay. And you can see that if CH is over the unity, we get a sizable Birefringence angle. And actually, it is consistent with the Planck data in this reddish shaded region. Okay. But if CH is much larger than unity, we get a negligibly small Barifringence angle. This is because the axion starts to move well before the recombination epoch. And in that case, we don't get any large Barifringence signal. Or if CH is much smaller than unity, then the axion never moves even after the matter radiation equality in that case. So even in that case, we don't get a large Barifringence angle. So we get we can explain the Planck data only if CH is over the unity. So although this is a very simple model, the prediction is quite non-trivial. And the right figure is the contour plot for the Barifringence angle as a function of CH and the anomaly coefficient, this one, times the initial misalignment angle. So we expect that this one and this one are over the unity. And in that case, we naturally explain the Planck data. Okay. So this is the phenomenology of this low energy EFT. But you may wonder if there are any simple UV origins of the effective mass term. So far we add this term by hand, but you may wonder if there are any simple UV origins. And actually there are, and we have proposed a couple of interesting models. So the first model is based on the non-minimal coupling to gravity. So one may write down this non-minimal coupling to gravity for the axion. And here the rich scalar is negligible in the radiation-dominated era because of the conformal symmetry of radiation. So this term is negligible in the radiation-dominated era. But in the matter-dominated era, R is of the same order with the Hubble square. So this leads to the similar effect to this term. So just by adding this non-minimal coupling to gravity, we get this effective mass term for the axion. So this is a very simple model. So the second model is based on the Witten effect on the hidden monopole dark matter. So suppose that there is an SU2 gauge theory in the hidden sector, which is spontaneously broken to an abelian gauge field, gauge symmetry by an adjoint Higgs field. So in this case, we have a monopole solution, and the monopole may be produced at the time of the phase transition. And those monopoles are good candidates for dark matter because they are stable due to the topological charge or magnetic charge. So let's consider the case that this hidden monopole is dark matter in our universe. Then if the axion couples to this hidden U1 gauge symmetry, then it is known that the monopole has an electric charge proportional to the axial field value. And this is known as the Witten effect. So this can be understood by writing down the one of the Maxwell equation, the Gauss's law. So if there is a chance-Simon coupling to the this U1 hidden gauge field and the axion, then the Gauss's law is modified in this way. So this means that around the monopole, we have a non-zero electric field, meaning that the monopole is diion with an electric charge proportional to this axion field value. Okay. So this implies that the axion acquires an effective mass in the monopole plasma to minimize the energy of the electric field around the monopole. If the axion field value is non-zero, then the monopole has a non-zero electric field, and it has a non-zero electric field energy. So in order to minimize the energy of the electric field, the axion should have a smaller energy. So this can be quantitatively written as a mass term for the axion. Actually, according to the Fisher and the Price scale, the effective mass for the axion in the monopole plasma is proportional to the monopole energy density. And if the monopole in the dark sector, in the hidden sector is the dark matter, then this can be written in terms of the dark matter density. So here the coefficient is given by this formula. And this is naturally over the unity if the axion decay constant is the Gatt scale, and if the gauge coupling constant in the hidden sector is of the same order with the standard model gauge coupling constant. So this is the UV complete model for this effective mass term. And this naturally explains why we have an order 1 coefficient for the effective mass term. Okay. So we have two possible UV origins of the effective mass term, and this low-energy EFT explain the Planck data. Okay. So this is the summary of my talk. So according to the recent analysis, the Planck data has a non-zero Barifringence signal. And this implies that the axion moves after the recombination epoch before present. But this would be a kind of a coincidence problem or why now problem, why the axion starts to oscillate at the present epoch. And we address this question, this coincidence problem, by introducing an effective mass term that is proportional to the dark matter density. This can explain this coincidence problem thanks to the coincidence of matter radiation equality and recombination epoch. So this is the idea. And this figure is the resulting Birefringence angle, and it can explain the Planck data with order 1 coefficient. And actually, there are a couple of yearly origins. These are proposal. So if the axion has a non-minimal coupling to gravity, we get this kind of effective mass term. Or if the axion has a chance-time coupling to the hidden photon with a hidden monopole dark matter, then thanks to the Witten effect, we get this kind of effective mass term. Okay. So that's it. Thank you very much.
Thank you for presentation, and thanks for timekeeping. Are there any questions or comments? I have a question about this non-minimal coupling. So this breaks the axion. Yes, this breaks the symmetry of the Pichet-Quinn symmetry.
Right.
So don't you care because the gravity is expected to break global symmetry?
Yeah, I hope that this comes from the fact that any quantum gravity breaks any global symmetries, like Pichet-Quinn symmetry. But I'm not sure if this one actually comes from such a quantum gravity effect. So I hope that one can check that this comes from, this has the origin of some Ilway physics.
Are there any other questions or comments? Oh, there is one from anonymous attendee. Is it possible to detect monopoles?
All right, that's a good question. So in the second model, we have a monopole dark matter. And the monopole has a self-interaction because we have a U1 hidden gauge interaction, which is not spontaneously broken. So the monopole has a self-interaction, and this kind of dark matter is known as a self-interacting dark matter. So this kind of dark matter is also motivated by the solution to the small scale crisis of the structure formation. So from that side, we can indirectly test this monopole dark matter. Okay, yeah. And this monopole is a hidden sector, so we cannot directly detect monopole in the standard technique of the standard monopole. Yeah. Thank you, Mark, for the question.
I have a quick question. Maybe you already explained. C gamma in this figure is somewhat larger than 1. And is it easy to obtain this kind of order 10-ish numbers?
All right, that depends on the model. So it depends on the Pichet-Quinn charges. So it can be arbitrary, but we expect that it is over the unity. But let me comment on another thing. So here we assume that the initial misalignment angle is equal to unity, but this can be as large as pi in principle. So in that case, C gamma can be 2 or 3 or something. And this can be seen from this right figure. So this combination can be of order unity to explain the Planck data. Yeah, thank you very much.
Thank you. Okay, then let's move on to the next talk. Let's thank Masaki for presentation.
Thank you very much.
Hello, can you hear me?
Yes.
Talk, right? Okay. Share screen. If I just do that.
So the next speaker is Neil Barry, and the topic is afflectine leptogenesis from Higgs inflation. Are you ready now?
Yeah, sure. Can everyone see it? You can see my cursor, right? Yep.
Yeah, I can see the cursor.
Okay.
So please.
All right. Thank you for the introduction, and thank you for PASCOS for having me. So hello, everyone. Today I'm going to be presenting a recent paper that myself, Cheng Han, and Hitoshi Miyama put on arXiv. I'd recommend going and have a look at the paper. So the basic idea is we wanted to see whether we can explain the three known issues of inflation, baryogenesis, and neutrino masses through the introduction of just a triplet Higgs to the standard model. So that's the basic idea, and I'll just do a brief sort of introduction. So as we all know, when we look at the universe, we see that there is a matter-antimatter asymmetry, which we parameterize by this equation here. We know that the standard model, although it can satisfy all the requirements to generate an asymmetry, is unable to generate a large enough asymmetry, being many orders of magnitude less than what we observe. So this is strong motivation that there must be some new physics that must be included. And one of the ways that it is commonly considered is the introduction of some complex scalar field, whether that be in, say, the usual acyclic mechanism, which is like the SUSY partners, and generating angular motion in those fields. So if you were to have some complex scalar field phi, and we have it charged under some global U1, so that might be lepton or baryon number, we can write down what the number density of that charge would be, dependent upon the dynamics of this scalar field. So the important thing here is that if we write it in this polar coordinate form here, we have this theta dot term, which means that we have to generate some angular motion in the field in order to generate an asymmetry. In order to do that, we require some lepton number breaking terms to be introduced into the potential, and that can also be seen through the equation for the evolution of the number density of phi, where you need some non-trivial introduction here, otherwise it will just evolve with the expansion dilution. So what we're going to consider here is if we consider this phi to be the triplet Higgs. And so the triplet Higgs is quite a natural extension of the standard model and is a key component of the so-called type 2 seesaw mechanism. So in this framework, we would have the standard model Higgs doublet here and some additional triplet Higgs given here. Now, the important part of for the seesaw mechanism here is the Yukawa coupling that can be written down between the lepton doublets and this triplet. And upon this triplet taking a VEV, you can generate the neutrino masses. Also through this equation, we can then define that the triplet itself is doubly charged under this U1L. So here we have a complex scalar field charged under some U1 global symmetry, which we'll call lepton number. And then also as a part of this model is that you immediately get lepton violating interactions between the triplet and the standard model Higgs. Here I've just written in the unitary gauge with the neutral components, but we have this cubic type term with this dimensionful mu coupling, which violates lepton number. And we also have what we've written down here is these high dimensional terms that could be possible, which here are these 5-dimensional terms. Now, yes, so basically we've got our ingredients here that we have potential lepton number violation, and we could generate this non-trivial motion of the angular momentum, angular velocity in the field. And we can also have this non-trivial VEV, non-zero VEV of the delta, which can generate the lepton masses, or the neutrino masses. So one other, so that's our first component of the model. And with the presence of these two scalars, we could also potentially use them in the context of Higgs inflation to set up this inflationary setting. So typically in the Higgs scenario, you consider the standard model Higgs cut with some non-minimal coupling to gravity. Through this non-minimal coupling, you get a flattening of the potential at large field values, which allows the setup of a Starobinsky-like potential, which is given here, which you can see that as chi becomes very large, this just becomes flat. And you can do the same thing if you have two fields, and you can get like a multi-field setup. And as I'll show later, you get a very nice inflationary trajectory here, which is just consistent with this Starobinsky-like potential. The Starobinsky inflationary setting has very good observational observational signatures, which are very consistent with current observation, as you can see here. So yeah, so that's very nice. So basically, I've just given a brief introduction here as to the different components of the model. So once again, we're trying to solve each of these three problems just through this single addition. The triplet Higgs and the Higgs doublet will play the role of the inflaton. During the inflationary and reheating phase, we're going to have some motion generated in the phase of the triplet. This will lead to some non-zero lepton number density by the end of these epochs. That lepton number density in the thermal plasma will be redistributed by equilibrium Saleron transitions, as in usual leptogenesis, generating a baryon asymmetry well before the electroweak phase transition. Later on, the triplet will take its VEV and we'll get neutrino masses. And the hope would be is that the parameter space of our model would be such that it could be potentially probed by collider searches in the near future. So now that I've just stated the framework, here's the actual Lagrangian. So we have usual kinetic terms, Einstein-Hilbert term, and we have our addition of non-minimal coupling here, which has the following form. And so I've written here in terms of just the unit to the neutral components. So here we have our lepton conserving terms, just the usual coupling, quartic couplings and so on. And then we have our lepton violating terms. So in order to proceed from here, we want to parameterize in terms of polar coordinates. And then we also want to define a mixing angle between the singlet components of these two scalars. So upon making these redefinitions, we come to this very simple, well, fairly simple equation here, which is just, we have a normal non-minimal coupling, and we have this motion, we have our motion here for the theta, which is coupled to the phi squared. And then we have our potential reduces just to the following. And we see that the lepton violating terms induce this cos theta type potential for the angular degree of freedom. So this is defined within the Jordan frame, and we're going to then convert to the Einstein frame, in which we recover just this Einstein-Hilbert term. And upon doing that, you find that, well, here's the equations, but what's quite interesting is that if you minimize the potential in this case, you find that the new degrees of freedom, which are this phi and alpha, the alpha becomes effectively fixed. So the ratio of these two fields becomes effectively fixed throughout the inflationary and potentially the reheating epoch, dependent upon the different couplings within the original potential. So these different couplings and the non-minimal couplings. Okay, so upon converting to the Jordan frame, the Einstein frame, we get our Starobinsky-like potential. We can convert between our Einstein frame field, Einstein frame field and Jordan frame field in the following ways. And so this is just the basic mechanics behind the setup we have here. And yes, okay. So what we're going to have is we're going to have this inflationary epoch denoted by this potential here. We're going to make various assumptions throughout. Firstly, we don't want the cubic term to dominate because we find that it leads to a very non-predictive behavior. But if the dimension 5 operator dominates over the cubic term just for these large field regime, then we can get a quite analytically nice result. We're going to assume an initial theta naught, but not, we're going to have a 0 theta naught dot. The mixing angle, as I said before, will be assumed to be approximately constant, and you can adjust this assumption for the reheating epoch. And then what we're going to assume additionally is that the dimension 5 term, although it dominates over the cubic term, it's not strong enough that it affects the inflationary trajectory that we've initially defined. And so these provide a few important constraints on the parameters. But now that we've done this, we can now solve both numerically and analytically the dynamics of theta. And so here, just jumping straight in, we can write down, like so from the equation I wrote before, defining the number density of phi that's induced. We can write that in terms of our complex scalar and theta dot here. And what we want to do is we basically want to find this quantity. And so we have our equation of motion for theta given here. So this is like our potential term, friction term, so on. And here is the actual numerical result for looking at the generated lepton number density. So there's a few key regimes here. So if you notice from here is where inflation, this is inflation. So in this plateau region and this uptick, and this is the transition to the oscillatory period and reheating. So the first regime here, you can quite understand quite well. So we started with some initial theta naught. So this term is non-zero, but the theta dot is 0. And basically, if you were to imagine that this theta is relatively small, you would find that this is just would be an exponential growth. So what we have happen here is at the very beginning of inflation, I should say this is coordinate time, we get this rapid growth in theta dot before it reaches some equilibrium point where you get an equilibrium between the friction term and the slope of the potential. And at this point, this drops out the acceleration, and you basically can define some terminal angular velocity. And so it's approximately flat throughout inflation, with most of this drop just coming from how this potential term evolves with time. And then once you enter this regime, the dynamics, the potential becomes smaller and smaller. 3 minutes. Okay. The potential becomes smaller and smaller. And so you end up getting this friction term domination. And if you just pretend that this isn't here for the moment, you'll see that if you solve theta dot dot, this multiplied by theta dot, this would just be theta dot on one, or it's some constant on phi squared, which means that you enter this sort of constant lepton number density regime. So, yeah, okay. So we basically can write down this analytical approximation, which after assuming the reheating is instantaneous, well, it's not really instantaneous, but there's no extra production of entropy. We get this simple equation for the number the asymmetry parameter, which is just dependent upon this dimension 5 coupling, the initial, and this non-minimal coupling. Now, this relation here with the tilde has alpha dependence, so, and that depends on whether the inflationary epoch is defined mostly by the triplet Higgs or the doublet. And yeah, so that there's a bit of parameter dependence here, but we can write down this fairly simple maximum asymmetry that's generated by just assuming that the dimension 5 term doesn't affect inflation. So it's fairly easy to produce the asymmetry. So now that we said we generate this asymmetry, we want to see whether we can do all these 3 things that we've claimed we can do. So we've got to take into this long list of potential constraints. We've got some successful leptogenesis. There's potential for washout effects here. So we want to have the coupling such that we don't wash out our generated asymmetry. We have the inflationary observables, which are given here. We have preheating constraints, so we don't have overproduction of in this theta degree of freedom during the oscillation. We've got isocurvature perturbations. We've made these assumptions that the mu is subdominant to lambda phi, the 5-dimensional term, and also that it's subdominant during inflation. We have constraint from the neutrino masses, and also subsequently the Yukawa couplings. So you can put in all these together. We can write down just an example set of parameters here. And what we get is this allowed region of parameter space where we can have successful inflation, successful leptogenesis, and neutrino masses. And what's nice to see is that we can have masses for the triplet that of order 1 TeV, 10 TeV. And as you can see, our parameter space is already being constrained by colliders. But we've got this nice parameter region here and quite a large region of parameter space. But yeah, so in conclusion, we've considered this simple extension of the standard model by just a triplet Higgs, well, I guess, and also nominal couplings, and we've been able to explain each of the inflation, leptogenesis, and neutrino masses. There's quite a lot of scope for potential constraints from colliders and possible other collider implications. And also, we didn't include here, but also vacuum stability. Yeah, thank you very much. I think that's on time.
Thank you, Neil. Are there any questions or comments? Oh. Masaki, go ahead.
So could you explain how the ice curvature constraint comes from? So you said that the theta must be smaller than 1 over NE or something?
It's going to be greater. So the theta, yeah, if it's too small, then you're going to have potential problems. Yeah.
Uh-huh.
Yeah. So yeah, that's something that we need to. Yeah, this is something we need to constrain here. Otherwise, if it's too small, you end up generating quite large isocurvature perturbations. But it's dependent upon the number of e-folds, as I say here. But we tend to consider, say, like 50 or 60. And so this constraint is like 10 to the -2 or 10 to the -3. This is, we followed the calculation done by Mark Hertzberg in his
I see, thank you.
Yeah.
Don't you have some visual representation of rotating field trajectory or something like that?
Oof, no, we don't have that. Yeah, we don't. Yeah, that's yeah. That probably would be a nice figure to have. Yeah, but you can see. I don't know. It's not really nice viewing here. Well, I'll put that together for you. I'll try and get that for you. Yeah. But it enters this approximately constant regime here, which is quite nice. It would just be like almost like this, which is the radius slowly reducing, I guess you could imagine here. This period is a bit more complicated, but then it enters another one of these regimes where it sort of doesn't really evolve too much. Yeah. So I guess you could imagine it going like this and then going like that. Okay. Oh, don't worry. Yeah.
Any other questions or comments? Maybe I should ask some stupid question. I'm not very familiar. After the creation of asymmetry, is it not equilibrate with thermal plasma?
So yeah, but that's where this washout assumption comes in. So yeah, you do have these lepton violating interactions, but we're assuming that they're small enough that you don't end up getting these washout effects. And that sort of comes in here. You see this plot here. The mu is too large. So the constraint on mu is actually very strong. So typically when you consider these triplet Higgs models, the mu is much larger than this, right? Like if the mass is larger. But so here we basically have this quite large constraint on mu, but nicely that's also consistent with the assumptions we've already made about the size of mu. But as long as you keep this mu not too large, you can prevent that washout occurring till it's already been too late for it to be a problem. Yeah.
It's great that after imposing so many conditions on slides.
Yeah, that's why I wanted to show that enormous list of things to be like, look at all these things we have, and it's still quite a larger infinite parameter space. Yeah.
Okay, so if there are no urgent questions, let's thank Neil.
Thank you very much.
And we will move on to the final talk of this session by Junya Kume.
Okay, so let me share the screen.
Yes. So he will tell us about chiral gravitational effect in primordial thermal plasma. Please go ahead.
Okay, so thank you very much for the introduction. I'm Junya Kume, a PhD student at the University of Tokyo. And today I'm going to talk about recent works on this chiral gravitational effect, which originates from the chiral gravitational anomaly. And okay, so this is the contents of my talk. And first, I introduce an example where the quantum anomaly becomes relevant to our universe as an introductory part of this talk. Yeah, so let's start. Yeah, this is just a simple reminder, but the quantum anomaly is the breakdown of this classical symmetry at the quantum level. So if you consider the massless QED, the divergence, you will have a non-zero divergence of the axial current, which is called the chiral anomaly. And this has quite important implication in particle physics. For example, this anomaly can explain the neutral pion decay constant. So, and now, how about in cosmology? You may come up with well-known example like electric spheron, where B plus cell anomaly in the standard model plays a role in particle cosmology. So here I'd like to introduce another example called chiral magnetic effect. So in the chiral asymmetric fermion background, which is characterized by this chiral chemical potential, here magnetic field can induce the electric current, surprisingly. And this proportional coefficient is actually fixed by the chiral anomaly. And this current causes the instability in a larger scale magnetic field. So it can be described as the origin of the seed magnetic fields, which can explain the observed galaxy magnetic fields and the galaxy cluster magnetic fields. Yeah, so including spheron, now you can see anomaly may play some role in our universe. But here I'd like to emphasize that we have gravitational anomalies. So let's see how gravity comes into matter. Yeah, so chiral anomalies evaluated from this kind of diagram that you can do the similar calculation for the case of external gravitons. And this results in a so-called chiral gravitational anomaly, where the contraction of the Riemann convergence tensor contributes to the axial current divergence. So now you see that gravity contributes. Then you may wonder why we are working on specifically this gravitational anomaly. And the answer is that, so this right-hand side means the helicity of the gravitational waves, roughly speaking. And this left-hand side corresponds to the chirality of the fermions. And the point is that in cosmology, we have both ingredients. So as you know, there are various sources of cosmological gravitational waves. And if you consider, for example, the baryogenesis, the primordial plasma should carry the chirality. So we can expect some non-trivial interplay between these two stuffs in cosmology due to this gravitational anomaly. Right, so in this situation, it is natural to consider some correspondence between this U1 case and the gravitational case. So this CME is a non-trivial interplay between gauge field and chiral fermions, which originates from this U1 chiral anomaly. So now we can consider some correspondence in this gravity side, which originates from gravitational anomaly. And actually, there was pioneer works on this effect. And so in this paper, the static fermion background with finite chemical potential was assumed. And they found this anomalous response due to the anomaly. So here, the gravitational wave, external gravitational wave induced the energy momentum tensor, which has a similar structure as the case of CME. like this here mu5 appears. So now you can consider some application in cosmology, like GWs propagating in primordial plasma. But it is not so straightforward because we can expect the chirality violation is dynamically happen in this plasma. So we need to take into account the non-trivial time dependence of background. And in our work, we show that such extension can be done by effective theoretic approach. So let me talk about this chiral gravitational effect in time-dependent backgrounds. But before going to that, let me start from the CME, because we can learn the essence of our discussion from this example. So, okay, so let's introduce the finite chemical potential term. Then, since we're interested in the dynamics of gauge field, let's integrate out these fermions. Then this leads to the induction of Chern-Simons term here. And yeah, this is just introduced for the convenience, which makes the more familiar form like Theta FF duo. Anyway, so the asymmetric fermion background caused the induction of Chern-Simons term. And okay, and now you can see how they contribute from the equation motion. And this term appears as the additional components of the electric current. And so now you can see here the CME is reproduced from this effective action. And the point is that, so the similar discussion holds for the case of graviton or the metric perturbation. And yeah, and here we also integrate the chiral fermions. Now we can see the induction of this gravitational Chern-Simons term. Yeah, so let's see how this contributes to the equation motion. And this left-hand side coming from the Einstein-Hilbert term. And here, this is the contribution from Chern-Simons term. And by comparing the usual Einstein equation, now you can interpret this contribution as an anomalously induced EMT. And it has this concrete form. And now you can see this part corresponds to the pioneer works, which assume the static fermion background or chemical potential. But here, I'd like to emphasize that mu5 dot dependence appears. So this treatment takes into account the time dependence of the backgrounds. Yeah, so now we can consider some correspondence between these two effects. So in the case of CME, the anomalous current caused the instability of the gauge magnetic field, and from such growing heredity of the magnetic fields, there's some back reaction to the fermion backgrounds. So let's see what will happen in the case of gravitational effect. So how this EMT modifies the gravitational waves and how they back reacts to the fermion background. All right. Yeah, so yeah, for concreteness and simplicity, let's expand the GWs in a circular polarization mode and consider the propagation in a specific direction like this. Then this is the equation of motion of the gravitational waves. And here, this lambda changes its sign with respect to the polarization mode. So now you can see this induced EMT causes the gravitational Biorefringence. But this is a general issue for the gravitational Chern-Simons term. This part contributes to the kinetic term of the graviton. So there is a strong coupling and ghost issue for a quite high momentum region. And to avoid such a dangerous region, we respect the parameter region like this. And we take and we treat this CS term perturbative. And with this treatment, this mu5 dot pert gives non-trivial correction because they change the dispersion relation. Yeah, so let's see. And so taking this plane wave as a zero source solution, we can evaluate the anomaly corrected solution like this. So here, so as you can see, so the non-zero mu5 dot is important for this case. So CME becomes non-trivial even just a constant but non-zero chemical potential. So here, non-zero mu5 dot is required for the gravitational case. So we need some external chirality changing process, but there is some examples in the cosmology like Biorefringence and Yukawa flipping interaction. So yeah, we can consider this becomes relevant in cosmology. And interestingly, because of this non-trivial phase factor, the information of such a chirality violation is accumulated on the helicity of the gravitational waves. Yeah, so we call this as a memory effect. And this is one important consequence from the CGE. Okay, so now we see the modifier dynamics of the gravitational waves. So let's consider their back reaction. But it turns out that in the case of gravitational effect, the back reaction is typically suppressed by this small factor, which is suppressed by this Planck scale. So we can do some perturbative discussion here. So assuming the presence of some external chirality changing process which dominates the whole dynamics of chiral chemical potential. And yeah, that part corresponds to this mu50. And you can consider some small modulation due to the back reaction, like this. And then from the anomaly equation, you can obtain a kinetic equation for the small modulation. And so due to the smallness of the back reaction, we can say that the memory of GWs, which memorize this dominant contribution, will not be spoiled. All right, so let's consider some example for this mu5.0. So this mimics some heavy particle decay, like Barifringence, and this results in this equation. So here, this is a dominant process coming from this term, but you can see some non-decaying oscillatory part. Yeah, so this is a kind of general feature in CGE, because so here this integration term remains as a source term even in later time. So you can say that this oscillation is coming from the early time memory of this dominant process. So we also consider the flipping interaction case, and here you can also see the late time oscillation with suppressed decay rate. Yeah, so now you can feel this this table with this correspondence. But let me make a comment. So this is not the end of story, because in the case of gravitational effect, the background curvature comes into matter. So for CME, fermions and gauge fields are conformal, so you can drop out the scale factor by field redefinition. But here, gravitons are not conformal, so scale factor explicitly comes into equation motion. So even for the case, some constant chemical potential is diluted by scale factor, the gravitational Biorefringence occurs. This is also the specific feature of CGE. All right, so let me make a summarize. So in this work, we consider the local contribution from anomaly with covariant Lagrangian, but there is also non-local effects was found in this previous work. So the extension for the time-dependent background for these non-local effects can be our future work. All right, so this is the summary. So the CGE is EMT induction in chiral asymmetric fermion background, and you can expect some memory effect and chemical potential oscillation. All right, so that's all.
Thank you for nice presentation. Are there any questions or comments? So let me ask about the wrong sign kinetic term at the UV. And is it the only feature for the gravitational case and not present in the electromagnetic case?
Yeah, exactly. And that is due to their spin structure. So, okay. So in our case, we can the effect of asymmetric fermion background results in this gravitational Chern-Simons term, and they have so the number of the derivative is different for the case of gauge field and this gravitational case. So in this gravitational case, because there are two derivatives, and so dispersed induced Chern-Simons term contributes to the factor of this kinetic term of the graviton. So the associated instability will be the ghost. So to make the consistent estimation, we need to avoid such a dangerous instability. But in the case of gauge field, because they have the less derivative than this gravitational Chern-Simons term, so generally this results in a tachyonic type of instability. So we can expect some enhanced effect in the case of this gauge field.
So what do you expect in reality? In high energy, maybe higher derivative terms become also important, and it may also affect the equation of motion. Or do you expect it's a, what is your viewpoint? It's an artifact or whatever physical interpretation about this ghost?
Yeah, we think such a ghost is really some, for example, quantum gravitational regime. So yeah, so in our calculation, we, as you can see, we consider the linearized gravity. So yeah, before so in such a ghost regime and strong coupling region, so this kind of calculation, the validity of this kind of calculation breaks down, so we cannot expect anything. So yeah, in our point of view, we want to not to consider such a dangerous regime.
I see.
Yeah, that's why we strict ourselves in where this term can treat it as a perturbative correction.
Thank you. Are there any other questions or comments? There is no talk after this, so we can ask. Okay, if not, then let's thank Junya. Thank you for nice talk.
Thank you.
So this is the end of the this session, and the next session will start at